My name is Anil. This is the second tutorial on fundamentals of semiconductor devices. So we will be looking at the whatever Digvijay sir has taught in the first lecture and the second lecture. Some part from the first lecture and some part from the second lecture. And if you have any doubts, you can ask me in between, or otherwise I will be keep moving on these slides. Okay. So you must have seen uh, in some textbooks or in your classes. So this is the isolated atom, and these are the these are the orbitals. These are the atomic orbitals in which the electrons are orbiting around the nucleus. Okay, so let us say this is the silicon atom. This is the silicon atom, and with the silicon atom has 14 holes and 14 protons in the nucleus, and 14 electrons which are there in these orbits. So there are some core energy levels. These are the inner orbits, and there are some valency cells, okay, valency orbits, which are not fully filled, and with these valency orbits are very loosely, the electrons in these valency cells are loosely bound to this nucleus or to the atom. Okay, so these electrons can be easily taken out of this atom by supplying some sort of energy. Okay, by some giving some potential, by giving by shining some light, or by external means. Okay, so these are like loosely bound, and if you see the potential energy diagram of this atom, this this at this place, this is the nucleus, and if you go this side or this side, any side of this is kind of a spherical. So any side, if you move away from the nucleus, the potential energy diagram will look like this. Okay, this the one has the very lowest energy, which means the to take out the electrons, it requires very high energy from the 1s cell, 1s, 2s, 2p, 3s and 3p. And if you write the electronic configuration of the silicon is 1s2, 2s2, 2p6 and 3s2, 3p, how much, 3p2, I guess, 2 charts, 2 to 4 or 6, 10, 10 and 4, 14. This is the 14. Okay, so these are the we can say these are the innermost cells, and these are the outermost cells, the third cell. Okay, this is the third cell, in which there are 4 electrons. 1, 2, no, not this one. 1, okay, 1, 2, 3 and 4. So these are this is 1s2, this is 3, no, this is 3s2, and this is 3p2. These are the valency shell electrons in this one. Okay, and okay, this is how the potential energy diagram looks like of an isolated atom. Okay, so let us see if how the band formation happens when these atoms, uh, this is the potential energy diagram of this isolated atom. So if there are other atoms that come close, let us say the two atoms come close to each other, these potential energies, these overlaps. Okay, these overlaps, that means there is an interaction of these potential energies, or we can say the electrons in these shells have some wave function. Okay, if we are not going that much deeper into that, into the wave function and this quantum theories. Okay, but the wave function function of these electrons sort of overlap, and or there is an interaction between the wave functions of these electrons, okay, in these outer shells. So what happens is, because of that wave function or the interactions, these electrons, okay, there will be a sort of energy will be like this, energies will be like this, okay, like this. So these outermost electrons can will no longer feel the kind of a well, okay. In an isolated atom there is kind of a potential well, this is the potential well, but these outermost electrons, when there is interaction because of the other atoms, so this sort of profile will be there, this sort of profile will be there, the potential profile. So these electrons are free to move this side and this side, so in the lattice, okay. So because these are free to move now, okay. So and now, and how what this happens is, there is some kind of there are electrons in the outmost shell, or in the cells of the in the orbitals of the atom, and there is nucleus, and there are some okay. So electrons here and the nucleus here, there will be an attractive force, and electrons here and electrons here, there will be a repulsive force, and these four forces, these three forces, there will be a balance of these four forces, attractive and repulsive forces, there will be a balance at a certain distance, okay, certain distance, that will be the we can say the interatomic distance, okay. So the two atoms will come close to the interatomic distance because of these attractive and repulsive forces. When the attractive and repulsive forces will be equal to each other, at that will be the interatomic distance, okay. And these forces can be ionic, there may be a covalent bonding because of that, and there are some van der Waals forces also, okay. And this thing we have already seen, the neighboring atom influences the potential energy in the solids. So whatever this we have seen here, there was one atom here, there was one atom here, because of that, if this atom influences the potential energy diagram, potential energy well of the other, potential energy of the other atom, okay. So this sort of profile that happens, okay. There is a, what we call it as a periodic potential, okay, periodic potential levels. And we have seen that wave function of the electrons in solids overlap, due to which the electrons are not only localized, okay, because of these electrons in the outermost shell, so they are sort of moving now. So the wave function of these the atom of the electrons in this atom and this atom, they sort of interacts with each other, and there is, because of that, there is splitting happens, okay, because of the interaction, because because of the Pauli's exclusion principle, no two electrons can have the same sort of energy, or cannot occupy the same energy state, okay, uh, unless they are of opposite spin, but we are talking with the same spin also. So no two electrons can have the same energy. Because of that, the energy if this is the shell, this is the energy level that splits into two, okay, that splits into two. If there are two atoms, from this one from this one, and these splits into, okay. Now okay, let's see the conductors, insulators, and the type of bondings. In NaCl, if you see, there are Na atoms and chlorine atoms. Na and NaCl forms because Na has the electronic configuration. One electron is in the valence shell. Okay, that, let us say, this is one electron in the valence shell. In chlorine, there is if it gets the one electron, it will get a stable electron electronic configuration. Okay, stable or noble gas configuration, it will be there. Okay, and if Na loses one electron, so it will go to the noble gas configuration, argon 10. Okay, argon 10 it will take, or so this is the thing. So if Na plus, and it is, there is a complete transfer of electron to the Cl. The Cl will take the electron. So when there is a lattice of the NaCl, so Na is surrounded by 6 chlorine atoms. Okay, and 1, 2, 3, 4. One is outside and one is inside. So there is Na is surrounded by 6 chlorine atoms. Okay, so there is a balancing of the force in between these. There is a balancing of the force in between the 6 atoms, and the same thing is happened with the, this is Na, this is Cl, and Ca chlorine also surrounded by 6 sodium atoms. Okay, so there is a balance of the forces in between Na atoms and the chlorine atoms because of the repulsive and the attractive forces. Okay, so this Na plus and Na plus is and Cl minus, so there will be a attractive force. So, and the repulsive force happens when these come too close, and there are electrons in the orbitals of the sodium and the chlorine, so they will repel each other. Okay, that will come to the interatomic distance. So now this chlorine has one electron and Na plus has one atom, one electron which is less in number. This is positively charged, and this is negatively charged. And this electron is very tightly bound to the chlorine. Okay, Na plus has the absence of electron, and which is, we can say it is positively charged, and so this is in stable electronic configuration. So chlorine won't, so in this case NaCl is kind of insulator, because there are no free electrons or holes in the lattice. Okay, Na plus do not have any electron or hole that is there, because it is in stable configuration, and chlorine Cl minus is also stable because this electron is very tightly bound to the chlorine. Okay, so this NaCl is insulator. Okay, so if we see the metals, let us say only sodium we can see. Let us say sodium, there is sodium has electronic configuration of 1s2, 2s2, 2p6 and 3s2, 3s1. Okay, this is the electronic configuration of the sodium. So this one electron is loosely bound to the sodium. Okay, sodium will try to convert into Na plus. Okay, this electron is loosely bound, which is in the valency shell. So it will lose one electron easily. Okay, so now if so many atoms of sodium will come close together. Okay, and from every atom you are getting one electron. Okay, and because of the interaction between the wave functions, so these electrons are delocalized. Okay, so you will see that these sodium atoms are immersed in the sea of an electrons. Okay, so these every single atom is giving you one electron, so this will act as a conductor. Okay, metals will this will act as a conductor, and because of that there will be a metallic bonding. Metallic bonding is because of this Na plus and the electrons in the surrounding. Okay, which are loosely bound and moving inside this inside the crystal, or we can say the lattice. Inside the lattice they are moving freely. Okay, these electrons which is donated by sodium because of the loose bound, they are loosely bound. Okay, and now let's move to the covalent bonding. In covalent bonding, if you see, let me check if someone is joining the group. Okay. Okay. Yeah. So in covalent bond in as NaCl there is a complete transfer of the electron. In covalent bonding there is a sharing of the electron in between the two atoms like carbon, silicon, and all these things, germanium. So these are sharing the electrons. Okay, so after sharing there is no matter which electron is belongs to which atom, which silicon atom. Okay, these are shared completely, and so there is a bonding in between them. And which type of bonding, like gallium arsenide and like compound semiconductors, as these mixed type of bonding, which you can say covalent as well as ionic bonding. Okay, so let's move. So the energy, okay, yes, the energy bands are formed when there is the attractive and repulsive forces balances at the interatomic spacing. So this is the relative spacing between the atoms in this direction. They are far apart. Okay, let us say this position, the atoms are far apart and they do not have any interaction in between them. Okay, the atoms are very far apart, so as they come close to each other, their wave functions, the electrons in the outermost shells interact with each other. Okay, electrons in the outermost shell interact with each other, and there will be a splitting of the energies, because these two atoms, let us say there are only two atoms. Okay, so what will happen is the outermost shell electrons will interact with each other, and let us say this is the 2s2 state. No, 1s2, 2s2, 3s, uh, P6, 3s2, and 3p2. These two states. Okay, these are okay. So in these, let us say these two electrons will interact of one atom. These two electrons of one atom will interact with the 3p2 electrons of the other. Okay, so we know that no two okay, as soon as they interact, they will have the same set of energy, because this isolated atom has 3p2, let us say px, py, and pz. Okay, so px has the same energy. Okay, if you see in the energy diagram, so 1s has some energy, 2s has some energy, 2p has some energy, 3s has some energy. So for all the atoms, isolated atoms, this won't change. This is the energy for all the isolated atoms. This won't change. This energy will be at the same level for all the isolated atoms. But as two atoms come close together, and the electrons in this level and the electrons in the other atom will interact, so they will have the same energy. Okay, but Pauli's exclusion principle says that no two electrons can have the same set of quantum numbers, or can have the same energy. Okay, so these two energy levels will split. Okay, one will have higher energy, one will have lower energy. These two energy levels will split into two. Okay, these two energy levels. So because of that, there will be there are only two atoms. If more and more atoms will come close to each other, let us say n number of atoms will come close together, so n energy states, they will split into an energy states. Okay, so let us say in this diagram, this is the for silicon, I guess silicon or whatever it is. It can be for silicon or carbon because they have shown these outermost energies only. Okay, it can be for silicon or the carbon as well, or germanium. So in this one, this is 2s state, let us say, no, 3s state. Let us say this is only silicon only. If it would be carbon, then it would be 2s. Okay, so in silicon, this is the 3s state, 3s orbital or energy state, and which has two n electrons, two n states and two n electrons, because of the n number of atoms we have. Okay, if we have n number of atoms, so one s orbital has two electrons and two states, because it can accommodate two electrons. Okay, so it has two states, and this is 3p. 3p has two electrons, but it can accommodate six electrons. So number of states, it has 6n states, but only 2n are occupied. Okay, so these come closer, and there will be an interaction in between the in between 3s 3p states of all the atoms. Okay, so there will be a split of the band, because uh, if there will be lesser number of atoms, so there will be not a band, but there will be certain energy levels. But there are some infinite number of atoms, we can say, we cannot count, so there will be a band of energy states. Okay, and at this spacing, this is the interatomic spacing at which these attractive and repulsive forces balances out, and at this there will be a band of, this is the band of energies which is fully filled, 4n electrons and 4n states, which is fully filled, and this is the gap in between the states. This is another band, which is the conduction band, and which is completely empty at this interatomic spacing. Okay, let me check if someone is there in the middle. Someone. So that is the band formation. This is the valency band. This is the valency band, and this is the conduction band. Okay, this is the minimum of the conduction band, and this is the maximum of the valency band. Okay, and this we will represent with this one. So this is the energy gap Eg, which is shown here, and this is the conduction band, and this is the valency band, and all these are shown at the 0 Kelvin. Okay, so at 0 Kelvin, because there is no, at 0 Kelvin all the electrons are at the lowermost energy states. As soon as we give some energy, some external thermal energy, so there is some chances, certain probability of going some electrons from the conduction, from the valency band to the conduction band. But this is the insulator in the sense the energy gap in between these two, the conduction band and the valency band, is very high. Okay, more than 6 electron volts, 5-6 electron volts. That is the insulator. Okay, in semiconductor, this energy gap is lesser. So if we give some external energy, let us say the thermal energy, or we shine some light from any source, so these electrons will jump from the valency band to the conduction band. Okay, so but at 0 Kelvin there won't be any energy, or any thermal energy, or we can say we are not giving any extra energy from any source as well. So then these the conduction band will be empty, completely empty, valence band will be completely filled. And in metals, what happens is, uh, this there the bands, if there are some energy, if there is some energy band gap is there, so one of them is partially filled. Okay, if there is some partially filled band, so there will be some states there, through which the electrons can move. Okay, let us say there are some electrons here. Okay, these are some electrons here. Okay, and above that there are so many energy states which are empty. So through the empty states, the electrons can move. Okay, these electrons can move. So then that will act as a metal, because they without any supplying the energy, or the electrons are already, electrons can move with just applying the potential. Okay, at 0 Kelvin. But at 0 Kelvin, if you apply a potential here, so there won't be any current, because is no there are no energy states available. So if electrons move, so there is, uh, at the same time other electron is moving in the other direction. Okay, so this is the theory. And last time someone asked about the direct and indirect band gap semiconductor. So if these are the this is the conduction band, this is the valency band. Okay, so this is the ek diagram, energy versus k diagram. K is the, we can say, the momentum, and this is the in the reciprocal space. Okay, not in the real space. This is the reciprocal space. ek diagram is the reciprocal space diagram. So in so if the energy, if the minima of the conduction band, this minima of the conduction band lies at for the same value of k where the maxima of the valency band lies. Okay, so the k value for these 2 points is same, so then this is the direct band gap semiconductor. Direct band gap semiconductor. Okay, so if the conduction band minima and valency band maxima lies for at different values of k. So whenever there is any transition happens, so there is a change in momentum. Okay, change in momentum of the electron. So what happens is, so from here, so there will be some energy will be released as some heat. Okay, to the phonons, so to the vibrations. Okay, so there will be, so this is the indirect band gap semiconductor if the k value are different for the conduction band and the valency band. Okay, and okay, so now let us see, whenever we see in the movement of electrons or movement of holes, so this is the energy E of the electrons. E of the electrons in the upper direction, energy of the electrons which is increasing, energy of the electrons is increasing, and this if in the other direction, this is the energy of the holes. Energy of holes is increasing in the bottom side, and energy of the electrons is increasing in the upper side. Okay, so these are some of the electrons which are jumped from the valency band to the conduction band. That can be through because of the thermal energy, or by shining some light, or by providing some external energy. Okay, so these electrons jump from the conduction band to from the valency band to the conduction band and left behind some hole. Okay, this is the hole. So it was supposed to be an electron, but there is no electron in this case. So there is a hole which is equivalent to a positive charge. Okay, which is equivalent to the positive charge, which was it was supposed to be an electron, but there it is not. And hole is a quasi particle. It is not a real particle, but it is a quasi-particle which is because of the absence of the electron. This is the absence of the electron. Okay, whenever we look the concentration of electrons or concentration of holes, we look for the concentration of electrons in the conduction band of a semiconductor, because electrons are moving in the free state, because these are there are very we will look into the density states as well. There are so many available states. Okay, so many available states. So these electrons can move through these states. Okay, and here these are empty. So whenever you apply a field, these electrons are moving from here to here. Okay, so this hole will move here, so there will be hole. So this the other electron will move at this the position of the hole. So there is a movement of the electrons, but the multiple electrons. So that can be considered as a movement of hole in the other direction. Okay, so but actually there is a movement of electron, not the hole, but it can be considered as a hole is moving, because there are multiple electrons are taking the place of the hole, not a single electron. Okay, so and whenever we find the concentration, let us say this is an intrinsic semiconductor. Intrinsic semiconductor means a pure semiconductor, pure silicon semiconductor, silicon or any semiconductor. So there is no doping, external doping, or there is are no defects in that. So in intrinsic semiconductor, so as so in intrinsic semiconductor, at 0 Kelvin, all the electrons are in the valency band. Okay, all the electrons are in the valency band, and there are no electrons in the conduction band. As we give some energy, some of the electrons will jump in the valency band, in the conduction band from the valency band. So there will be some electrons. Okay, as many as electrons will jump from the valency band to the conduction band, so they will leave behind a hole. Okay, so in case of the intrinsic semiconductor, that can be the concentration of electrons Ni. N represents the number of electrons, or we can say the concentration of electrons per centimeter cube. Ni is equal to Pi. Pi is the concentration of holes, number of holes per centimeter cube. Okay, so these will be equal for the intrinsic semiconductor. Okay, because as many as electrons are jumping from the valency band, so they are leaving behind some holes. Okay, some holes. So the equal number of holes will be left behind. Okay, let me check if someone is also join. Okay, so if you see, this is the electric field in a semiconductor. If you apply an electric field in a semiconductor, and so let us say this is the this is the distance. Okay, this is the distance, and you apply, and this is the energy E. Okay, total energy. This is the total energy E. So this is the valency band, this is the conduction band, and when you apply some field, so the field is such that there will be a gradient in the conduction band and the valency band. These are the conduction band, this is the valency band, this is the conduction band, and there will be a gradient because of the application of the field. Okay, or when, or in another words, if this is the semiconductor material, let us say this is the distance, and this is the width of the semiconductor material, and you apply a potential. Let us say this is the okay, this is the positive, this is the positive, and this is the negative. So if you apply a field, electrons will move in this direction. Okay, electrons will move in this direction. Okay, there is an application of the field. This electric field direction direction E, or whatever you call, because E we are representing with energy, so you can say this kind of E, psi or C. The electric field direction is in this direction, so electric field direction is in this direction. This is the electric field which is applied in this direction, and there are some let us say these are the electrons at this position. They are moving in this direction, okay, because electrons are moving in this direction. Electrons from the higher energy to the lower side, electrons always move from the higher energy towards the lower energy whenever you apply a field. So this is how the band diagram looks like. Okay, whenever you apply a field, there is a gradient in this in the conduction band and the valency band, and this is because of the application of the field. Okay, and okay, so this is because of the application of the field, and there will be some potential change. This is the change of nothing but the change in potential. Okay, this is the change in potential. Conduction band and valency band gives you the potential change. Okay, this is the change in the potential, this is the energy. Okay, and can you see this parabolic curve? This parabolic curve is nothing but the energy band diagram of of the semiconductor. Okay, whatever at this position is the energy, the potential energy, the kinetic energy at this position, at the bottom of this parabola, so is equal to 0. Whatever the electron will be there at this position will be 0. Okay, if the electron is at any other position other than the bottom position, bottom of this EK diagram, okay, so that there will be some kinetic energy. Okay, this gives you the potential energy. There will be some potential energy at this position. This gives you the bottom of the EK diagram. Okay, this energy band gives you the this is the trace of the bottom of the of the EK diagram. Okay, and so whenever there is an electron which moves inside the lattice, okay, it gains some energy. If it is gaining some energy, there will be a kinetic energy associated with that electron. Okay, so if the electron is moving from this position to this position towards this direction, okay, because it must move because of the application of the electric field, and if there is an electron, it must move. Okay, so electron is coming to this direction, so it is gaining some kinetic energy. Okay, it is gaining some kinetic energy. So whatever electron at this position at okay, this is the position, in the lattice. Whatever the electron at this position in the lattice, okay, this is the semiconductor, let us say. At this position in the semiconductor, that will have some kinetic energy, and that kinetic energy is this one. Okay, that kinetic energy is this one, which is the this is the kinetic energy. Okay, this is the potential energy. Above potential energy there will be the kinetic energy, and at this position, if you didn't get anything from this one, you can ask me, because this is sort of important for the charge transportation inside the semiconductor, how the charge transportation happens, and how the different is the EK diagram and the Venn diagram. Okay, there are two things in this one. One is the EK diagram, which is the reciprocal, is in the reciprocal space. This is the EK diagram of at this position, okay, this is the EK diagram at this position, okay, for this position, and this is the band diagram of the semiconductor in the space. This is the band diagram in the space. So this is the semiconductor, and you have applied a potential which is, this is positive, this is negative, like this. Okay, across these two kinds you have applied the potential, and how the electron is moving inside inside this semiconductor is shown by this figure. Okay, so how the kinetic energy is associated. So there is electric field. Because of that electric field, there is some some kinetic, because there is some gradient in the conduction band and this valency band. Okay, and also electron are going this side, and also there are the holes associated with this. Okay, so this is the valency band for that same, and the holes are also moving in this direction. So upper side hole has the least energy. Holes will also always move from the bottom to the top. Okay, so this is kind of a bubble in a bottle. Okay, if there is some bubble in the bottle, that always will move from the bottom to the top. So this is the same thing. Okay, and so there is during this process there is scattering. Okay, so this cannot get too much of kinetic energy and this thing, because as soon as an electron moves inside a semiconductor, it will encounter some other atoms and it will scatter. So when it will scatter, the kinetic energy will come down. Okay, will come down, and this is how it is shown, the kinetic energy. Okay, I will take the black pen. So this is how the kinetic energy is. I will take some. Okay, no, I hope you got this. If you didn't get, you can ask me, or if you want to ask me in the next class, you can ask me in the next class as well. It is a sort of important also. So now let's move to the concept of the effective mass. Effective mass. So you must have seen this kind of the EK diagram. Okay, this is the EK diagram for the electrons. Okay, or this is the conduction band. This is the conduction band. This is the minima of the conduction band, and this is the direction. This is the K, which is the which gives the momentum of the electron. Okay, so the energy associated with the electron is given by E is equal to half mv square, or this is given by p square by 2m. Okay, this is given by p square by 2m, and if you with the de Broglie wavelength, you convert this p to h square, h cut k. So the energy E is nothing but the kinetic energy. The kinetic energy is given by h cut square k square by 2m. Okay, this energy, and now if you double differentiate it, there will be so it will be d2e by dk square. And if you see this band diagram, this is the not the band diagram, this EK diagram. Yeah, this curvature carries all the information about the lattice. Okay, this curvature carries all the information, how this curvature will look like this, like this, however it look like, it carries all the information about the lattice. Okay, so what is the spacing kind of, and in all, so this is shown in the two-dimensional. Okay, so it is in the three-dimensional. If you look at or if there is a perfect kind of crystal which has equal spacing in all the direction, it will look like this only. That will look like this only. We can say some like cubic lattice. Okay, so because all the atoms, if you take any atom, you will in any direction you go, you will see an atom at the same space, same distance. Okay, but if you have hexagonal close packing, or some other kind of structure, so in that case, so if the electron moves in the vertical direction or in this horizontal direction, it will encounter a different set of potential wells. Okay, the different different set of potential wells, we can say periodic potentials will be different in all these directions. So this curvature will change with the direction, so the effective mass will change with the direction. So what we say is depends, the effective mass depends on the direction of motion of the charge carrier in the crystal. Okay, the effective mass is given by, this is the what we calculated from this curvature d2e by dk square. You can calculate with, you just can differentiate whatever this curve is. Okay, so there will be some uh, there will be some equation of this curve, and you just double derivative, you will just get a double derivative, and from that you can calculate the effective mass. This effective mass carries all the information about this curvature, and this curvature carries all the information about the lattice, and so this effective mass is very very much important. Okay, so if, let us say, if there are some curvatures. Okay, let us say this curvature, this is one curvature and this is another curvature. This is A, this is B. The curvature of A is more than the curvature of B. Okay, so more the curvature, less will be the effective mass. Okay, more the curvature, less will be the effective mass. If the effective mass will be lesser, so whatever the particle, electron or hole, if the effective mass is lesser, so it will feel a less perturbation, or what we can say, it can move easily. Okay, it can move easily inside the lattice if the effective mass is lesser. Okay, so the mobility will be higher. Okay, less the effective mass, more will be the mobility. Okay, more the curvature, this, the A has more curvature, B has less curvature. More the curvature, less will be the effective mass, more will be the mobility. Okay, so this is the thing that I wanted to tell. So let us see with the intrinsic and extrinsic materials. So in the in intrinsic semiconductors, so that we've already seen. So in intrinsic semiconductors, there are some this is the conduction band, this is the valency band. So there is no external doping, so there are no impurities. So whatever electrons are excited from the conduction band are there only. These are the only electrons which are in the conduction band which are excited from the valency band. So so this N is equal to P. So at any temperature, at any condition, so number of electrons and number of holes will be equal in the semiconductor. Okay, in the conduction band and the valency band, not in the semiconductor. In semiconductor, there will be, when we dope it at that same time, because of the charge neutrality, the electrons and protons should be equal. Okay, and that is the different case. So let's say this is the silicon atom. Silicon is connected with another silicon with these bond, which is these are the two electrons. Okay, the bond represents the two electrons. Okay, so when we supply some energy, to this lattice, there at T is equal to 0 Kelvin, there these all the bonds will be intact. Okay, all the bonds will be intact. As we increase the temperature, there will be some breaking of bond, and that breaking of bond is the same as the transferring of electron from the valency band to the conduction band. Okay, and these are the free electrons and holes which are free to move inside the semiconductor. Okay, so these are the only electrons and holes inside the semiconductor, and which are intrinsic semiconductor, and these will be equal. N is equal to P is equal to Ni. Ni is the intrinsic, N is the concentration of electrons, P is the concentration of holes. Okay, at T is equal to 0 Kelvin, so there won't be any electrons in the conduction band. Now let us see if there are some of the let us say this is the extrinsic semiconductor, which is if the which is the n type. This is n type. I will tell you why this is n type and why this is p type. Okay, this is n type. So the conduction, so when we dope a semiconductor, so we can create the number of electrons in the conduction band, we can raise the number of electrons in the conduction band, or we can increase the number of holes in the valency band. Okay, so if we are creating number of electrons in the conduction band, more number of electrons in the conduction band, then this is an n-type semiconductor. So this ED is the defect level. Okay, this is the energy level of the defect that we have created by doping, or we can say this is the doping level, doping energy level. Okay, so we have doped this semiconductor with some n type of the dopant. Okay, so this as soon as we give at T is equal to 0 Kelvin, these there won't be any excitation, because the okay, if you see in between EC and ED. Okay, I'll just remove all these things first, so that you can see. I will take this red pen. So the energy difference at this position, the EC and ED, there will be very small energy difference. As soon as you increase the temperature T by very small amount, so these electrons in the defect or at the donor level will get some energy and will be transferred to the conduction band. This is what it is happening here. A very small energy is required to increase the concentration in the conduction band if we dope the semiconductor, and this is happening. And at room temperature, it is believed that all these electrons are transferred from this donor level to the conduction band. Okay, so these electrons transfer from at this donor level to the conduction band at some T is equal to, here it is given 50 Kelvin. At 50 Kelvin, they are just transferring, because a very less amount of energy is required when we dope the semiconductor. Okay, so if you increase the temperature further, if you go to, let us say, 300 Kelvin, some of these electrons also go from this valency band to the conduction band. Okay, and so both will be there, some intrinsic also and extrinsic also. And this is the p-type semiconductor. P-type semiconductor is known as because if when we dope the semiconductor, if it can create some holes in the valency band, this is the acceptor level. Okay, EA is the acceptor, ED is the donor level. Donor, and this is the acceptor energy level. Acceptor in the sense it accepts the electrons. Donor in the sense it donates the electrons. That's why the donor. Okay, when we say this any semiconductor is doped with the donor impurities or acceptor impurities, we are saying that if the donor impurity, if we say the donor impurity, it is the p type, if it is the n type semiconductor. If we say the acceptor with a semiconductor is doped with the acceptor impurities, then that is the p type semiconductor. Okay, this acceptor level is energy level is very close to the valency band. Okay, so when we give some energy, so these acceptor level, some of the electrons can be transferred from this the valency band to the acceptor level. Okay, there will be some density of states of this acceptor level. Okay, there will be some density of states, and this if the this gap is very less, so that density will be completely filled. Okay, that's in the same case here. So at donor level there will be density of states, and which is fully filled at 0 Kelvin, and all the electrons are transferred from the donor to conduction band at some temperature. Okay, so this will be fully empty after that. Okay. So now I hope you got the point whatever I am telling. So if you didn't get anything, so you can just ask me now. Okay. So, so now we can we have seen the conduction band, valency band, and now we we can we can calculate the concentration of the electrons or concentration of holes in the semiconductor. So when we calculate the semiconductor concentration of electrons and holes, we require the Fermi-Dirac distribution. So in Fermi-Dirac distribution, what we will look into the subsequent slides. What is the Fermi-Dirac distribution, and what is the basic definition of that? And then we need the density of states. Density of states, how many states are there in the semiconductor? Okay, either filled or empty or whatever it is. But whenever we say the density of state, we always look for the empty density of states. Okay, so we will see that. And density of states in the conduction band, and of which can occupy the electrons. Density of states in the valency band, which can occupy the holes. Okay, and then we will go to the electron and hole concentration at equilibrium. Okay, we will see that thing. So the Fermi-Dirac distribution function is nothing but it is the probability of finding an electron at the energy state E. Okay, if this is the okay, these are the energy states. Let us say the probability of finding an electron at this energy level is the nothing but the Fermi-Dirac distribution gives the probability. Okay, this Fermi-Dirac distribution will give the probability whether what is the probability that an electron can occupy this state. Okay, an electron can occupy this state. So, or we can say the probability of occupancy of anything by the hole or by the electron, and that is the probability of occupancy. Okay, this Fermi-Dirac distribution is given by this formula. Fe is equal to, this is the probability of finding an electron at energy E. Okay, or probability of occupancy of the energy level E is given by 1 by 1 over 1 plus e raised to power e minus ef by kt. This ef is the Fermi level. Okay, we will come on this as well later, but you can say this gives the extent of we can say extent of electrons in the conduction band, or extent of holes in the valency band. Okay, how the Fermi level moves in the band gap can give us the extent of the electrons or holes in the conduction band and the valency band respectively. Okay, so this is the formula that is given. This is the Fermi-Dirac distribution. Okay, and in so now what is the probability of finding an electron at the Fermi level itself? Okay, let us put the E as EF. If you put the E is equal to EF, so there will be 1 plus E minus EF is equal to 0. 0 by kt, e raised to power 0 is 1. Okay, e raised to power 0, 1 plus 1 is equal to 2. This will be equal to 1 by 2. So probability of finding an electron is 1 by 2 at Fermi level. So irrespective of temperature, whether whatever is the temperature, so the probability is always 1 by 2 at Fermi energy. Okay. So now okay, so now if you look at, okay, so this, if you see 1 over 1 plus e raised to power e minus ef by k. K is the Boltzmann constant, KBT, or you can see KBT. KBT is the KB is the Boltzmann constant. So if E is this energy, E is less than EF. Okay, energy is energy level, whatever the energy level is less than the Fermi energy. This whole term will be negative. Okay, this whole term is negative. Whatever we are looking for the for T is equal to 0 Kelvin. Okay, T is equal to 0 Kelvin. Okay, so this term is negative. This term is negative. KBT is equal to 0. So what will come is 1 over 1 plus e raised to power negative of something, negative of some constant k divided by 0. Okay, this will go to minus infinity. E raised to power minus infinity is what? Okay, that is 0. E raised to power minus infinity is 0. Okay, e raised to power minus infinity will be 0. So 1 over 1 plus 0 is equal to 1. So the probability of finding the electrons in all the states which are less than EF. Okay, or we can say the probability of finding an electron in less than EF is always 1. Okay, in other words we can say the all the states are occupied at 0 T is equal to 0 Kelvin below EF. Okay, below EF all the states will be occupied, and above EF at T is equal to 0 Kelvin will be 0. All the states will be unoccupied. Okay, so probability of finding an electron above is 0. So if you put E is greater than EF, so there will be positive something, and KBT is 0. So there will be e raised to power infinity, e raised to power plus infinity. So that will come out to be 0. Okay, this is the thing. So if you increase the temperature, okay, let me clear it out. If you increase the temperature T, if you increase the temperature, well, so whatever it is, so for less than EF or whatever, so there will be this Fe, the probability function with E will move this side. Okay, so there will be a but what we have seen, irrespective of temperature, this Fermi level, the probability of finding an electron at Fermi level will always be 1 by 2. This will be 1 by 2, and if you increase the temperature, there will be a shift in this graph like this. Okay, you will get to know more when we you solve some problems on this, and I am following Banerjee and Streetman's book, so you can also look into that if you want to go much more deeper into these things. So you can go through the Banerjee and Streetman solid state electronics book, I guess. Let me check the name of that book. So be some, I don't remember. Yeah, solid state electronic devices. So now if you see, okay, let us if let me check what is we should come on this, I think, later. Okay, let's go through this a bit. So this is the intrinsic semiconductor. So this is the distribution, and this is the energy, and this is the conduction band, this is the valency band, and this is the kind of the energy of the electron, or we say this is the energy profile. Okay, this is the valency band, this is the conduction band, and in between there will be a Fermi level. Okay, so at Fermi energy, this this is any temperature T is equal to some temperature, let us say 200 Kelvin. Okay, let us say 200 Kelvin. The Fermi distribution will be look like this. Okay, so uh, this at energy EF is the Fermi energy. At EF there will be the probability of finding an electron is 1 by 2, and at this position, the probability of finding the electron will be very less. Okay, so this is that probability. These dots are showing some of the electrons are there, because as soon as we increase the temperature, there is a certain probability of finding the electron at this. Okay, this certain probability, this is not equal to 0 is this one, but this is certain probability. So this will give you some electrons. Okay, some electrons in the conduction band. But if it is doped with the n type, so there will be some the energy, Fermi energy will be shifted up, and the concentration of electrons will be more in this case, and concentration of holes, if you see at this position, the probability of finding a hole, or the probability of an unoccupied state. So whenever we say Fe is the probability of finding an electron, okay, in the conduction band, 1 minus Fe is the probability of not finding an electron. That is the probability of not finding an electron. That means that is the hole. Okay, it is unoccupied, and this gives the whole probability in the valency band, and this is the 1 minus Fe. If you see here, this is the 1 minus Fe, and you will get this point. This is 1 minus Fe. This blue graph is the 1 minus Fe, and this is the probability of not occupied state. Okay, if there is not occupied state, that means there is hole, and probability of finding a hole is more than probability of finding the electrons in the conduction band. So that's why the concentration of holes is more than the concentration of the electrons in the p-type semiconductor. Okay, and in the n-type semiconductor, the concentration of the electrons is more. But whatever I am telling you is the effect of the doping. Okay, but this Fermi level moves up because of the doping. Okay, because of the doping. So if you in any semiconductor, when we solve the problems, we always see the level of the Fermi level, and then we calculate the number of electrons. But it should be ulta. We should check the number of electrons, and then we should calculate the Fermi energy. But to know the Fermi energy level, it is very easy. So that's why we go in another way. Okay, so you will get this thing when you solve the problems, because you will be provided all the things that are related to the EF, but you don't know the number of electrons. Okay, the number of electrons calculation will be very easy if you just know the Fermi energy level. And let me check. Okay, so now electron and hole concentration at equilibrium. So what we have calculated, the probability of finding the electron. Okay, the probability of finding the electron is Fe. Okay, which is given by this function Fe. Okay, this is the function, this is the energy E which is given, and this is the Fe exactly in the middle of the conduction band and the valency band. Okay, so and this one more thing we require is the density of states. Density of the states is the number of states which are available to take the electron. Okay, number of states which are available to take the electron. So Fe is nothing but, if we say, total number of electrons n, or say divided by Na. Ne is the number of states. So it is sort of that Ne or Ne into De. De is the De we are taking, because this is Ne is given by per unit energy terms, and De is the range of the energy that we need. So N, we are calculating N is equal to whatever the number of electrons in the conduction band is per centimeter cube. Okay, this N is per centimeter cube. Okay, the density of states Ne, this Ne is given by some in some books. This Ne is written, or Ge is also given in some books. So both are same. If you see this is the density of states. Ne or Ge is the density of states per centimeter cube per unit energy electron volt, ev minus 1. Okay, if you multiply it with the De is the range, a very small range. This is the De. Okay, this is the De. If you multiply with that, just remove this one. So that is the density of both with the different units. Okay, so this Ne into De is given by this formula. Okay, this is Ne into De is given by this formula. So if you multiply Ne into De into Fe, this is the okay. This is the Ne. This graph is the Ne into Fe. This is the Fe is the probability. If you multiply both these, you will get the number of electrons. And if you integrate it from the conduction band, from this point to the infinity, okay, from this point to the infinity. So these are the density of states to the infinity. Multiply this probability of finding the electron in these states, so you will get the concentration of the electrons. Okay, so this is the concentration of the electrons. This is concentration of holes. If you multiply this with this one minus Fe. Okay, so and this was for the intrinsic semiconductor. So this is not that much typical, but I went through direct formulas, so you might be thinking it is a bit difficult. But calculation of the density of states, it will take account of the, I need to tell you about the Schrodinger equation, and from that we will go to the reciprocal space, and from that reciprocal space we will calculate the density of states in k space, and then we will convert that into the real space, and it will be a bit longer, but if you go through through the books, you will get it easily. Okay, if you won't understand, just let me know. I will tell you about that. I'll prepare for that. Just tell me. Okay, so these are the things. So this is for the n type, and this is for the p type. In n type, there will be concentration of electrons in the conduction band will be more, because the probability will this Fe will shift it up because of the EF level. Okay, EF level is more, so the probability of finding the electron in the conduction band will be more. So probability is more, and so but the density of states the same, but the overlap will increase. Overlap of the of this Fe function with this density of states will be more. So this is nothing but the multiplication of these. If the overlap will be more, the concentration will be more. If the overlap with this and this will be more, the concentration of holes will be more. Okay, so this will be a p-type semiconductor, this will be n-type. This is the intrinsic semiconductor. Okay, so now okay, let me just erase this thing. So now the concentration of electrons in the conduction band. Okay, this is the valency band, this is the conduction band of a semiconductor. So the conduction so when you solve that previous equation, this equation, you will get something n naught is equal to some big term, some sort of big term, and FEC. FEC is nothing but this is the finding the electron at the conduction band, minimum. Okay, that is the thing. And NC is nothing. NC is the density of states or effective density of states. If you see that this is the EK diagram, in the EK diagram this is energy, this is the K, this is E, this is E, this is the bottom of the conduction band. And when we say there are electrons in a semiconductor, most of the electrons lie at the bottom of the conduction band, and whatever be the portion or because this is not exact parabola. If you go through the potential or periodic potential, there will be a distortion that you must have seen. There will be some distortion in the EK diagram. So but at this bottom of the conduction band, this is the first Brillouin zone, and the bottom of the conduction band can be regarded as a perfect parabola, and most of the electrons will be at the bottom of the conduction band, because bottom of the conduction band is the least energy, and that's why we can consider this thing NC into FEC, and this is the N naught or N naught is the concentration of the electrons in the conduction band, and they lie at this bottom of the conduction band. Okay, and the same thing is with the holes. Holes will lie at this bottom of the valency band. The bottom of the valency band is at this, or we can say the top of the valency band, not the bottom, at the top of the valency band, which is a perfect parabola for a certain value of K. Okay, because of this, and this FEC, the function FEC, or this is the Fermi-Dirac distribution, or when whether this the states at EC will be occupied or not. Okay, so this is given by this, and this can be approximated e raised to power minus EC, or this thing, and if this the energy gap EC minus EF is very less, or less than 3 kBp. Okay, this EC minus EF, what I am trying to tell you is this thing. If this, let us say, this is not an intrinsic semiconductor, it is doped with the N type of impurities, so there will be there will be EF, Fermi level will be close to the conduction band. In that case, what will be the concentration of electrons in the valency, in the conduction band? Okay, that will be can be calculated with this formula, and F of EC will be this thing. So, but this formula will only be applicable, and note, this formula will only be applicable if the difference between this EC minus EF, the difference between the conduction band and the Fermi level, conduction band level and the Fermi level will be greater than 3 kBp. Okay, 3 times of the Boltzmann constant, and this kBp value is 0.026 electron volts. this is the thing. And NC, the effective density of states, is given by this formula. And NC also varies with the temperature. NC varies with the temperature, and the same thing happens for the whole concentration. The whole concentration is given by the NV. NV is the effective density of states in the valency band at this position, at the topmost of the valency band, and this is nothing but the probability of not finding an electron, or probability of the empty state, finding an empty state in the valency band. Okay, so this can be approximated to this. And when okay, let me tell you this thing as well. So this is the conduction band, this is the valency band, valency band. So if concentration of holes we calculate when there is the doping, or let us say not doping. So and let us say this is the EF, this is doped with the p dopants. So the difference in between these two must be greater than 3 kPa. Okay, so then only you can apply this formula, otherwise you have to apply this one only. Okay, so instead of this one, so P naught is given by this, and V is given by, and V is the effective density of states. Okay, so more things. Okay. Okay, so Ni. So from that formula we have calculated previously N naught. N naught is the concentration of electrons. P naught is the concentration of holes at equilibrium, and this is not for, we have not written EI. EF is the Fermi level that can be at any position. It is not need to be the intrinsic semiconductor, but it can be any. It can be intrinsic, it can be doped or undoped, anything it can be. Okay, so now let us see for an intrinsic semiconductor. In intrinsic semiconductor, if n, this is the Ni, intrinsic carrier concentration, which is equal to Nc into e raised to power minus this thing. This can be applicable because in intrinsic semiconductor the Fermi level is at the middle, so this formula can be easily applicable. So this is the whole concentration, intrinsic whole concentration, which can be applied. Okay, so now so in the previous case, this N naught and P naught that we have calculated, N naught and P naught, just multiply these two, the what will come out, we will see N naught into P naught is equal to Nc into this formula that will be Nc into Nv e raised to power minus of Ec minus Ev. So this is nothing but the band gap, easy. So when you solve these two by multiplication, whatever is in the power of E, that will be added together. Okay, that will be added together, and you will get this formula, Nc into Nv into e raised to power minus of Ec minus Ev by kT. So what you will get is, from this is the Eg by kT, Nc into Nv into e raised to power minus Eg by kT. So this is the N naught into P naught product. You get this thing. Now multiply the concentration, the intrinsic carrier concentration of electrons and holes. So you will get the same thing, Nc into Nv into e raised to power minus Eg by kT. So but N is equal to P, Ni is equal to Pi for intrinsic carrier concentration, Ni into Pi. Ni square is equal to Nc into Nv into Eg by kT. So Ni will be square root of this thing. Okay, this is the intrinsic carrier concentration that you can calculate of any semiconductor at temperature T. You need to know about the Nc and Nv, that most of the cases Nc and Nv is given, and if not given, you can calculate from this kind of formula. Okay, This is the formula. For that you need to know the Mn star or Mv star, which are the effective masses of the of the electrons and holes. Okay, so this is the thing. N naught into P naught is equal to Ni square. This will hold everywhere in an equilibrium condition. Okay, so in any semiconductor, whether it is doped or undoped, so N naught into P naught will always be equal to Ni square. Okay, so if you are given with the whole concentration, you can easily calculate the electron concentration or vice versa, and also you can calculate the band gap from this thing. If you are given this thing, also you can calculate the Fermi level. Where is the Fermi level if you are given any of the carrier concentration? If any of the carrier concentration you are given one carrier concentration, if you are given, you can calculate a lot of things out of that. Okay, so temperature dependent carrier concentration, this we will see later, or I just can go through a bit from this one. But this is the time temperature axis T. So T is, which is 1000 by T, which is the Kelvin inverse, which is the opposite. So this side is the lower temperature, this side is the higher temperature. Okay, so and this is the carrier concentration. This is the carrier concentration, and this graph is taken at various temperatures, and how the carrier concentration looks like with the at various temperatures. So the carrier concentration versus inverse temperature, or silicon is doped for 10 raised to power 5 donors. Donors is the N type. Okay, N type semiconductor with 10 raised to power 15 centimeter per centimeter cube. Okay, this is the carrier concentration or the donor concentration, not the carrier concentration, because we cannot say the carrier concentration because we are going at the low temperatures. At low temperatures, these are not ionized. Okay, how this will be look like, as we have seen two things. As we have seen, so there will be a, so this is the donor, so this is the ED, donor level, ED, donor level. Okay, so at where T is equal to 0 Kelvin, T is equal to 0 Kelvin, what will happen is all these states will be filled, so there won't be any carrier concentration in the conduction band. Okay, this is the conduction band, this is the valency band, so there won't be any carrier concentration in the conduction band, because at T is equal to 0 Kelvin, all are immobilized, all the charge carriers are immobilized, and they are not ionized here. As soon as we increase the temperature a bit, let us say 10 Kelvin, so some of these will get ionized, because if you see Fermi-Dirac distribution, okay, I'll plot that Fermi-Dirac distribution so you will get easily. Okay, so this is 1, this is 1 by 2, and this is EF. Okay, so as we increase the temperature, so it will be like this. Okay, it will be like this. So there is some probability, so this can excite. Okay, there is some probability of finding the electrons at this position. So if we increase the temperature more, it will go more this side, so the probability will increase, the probability of finding the electron will increase, so more and more charge carriers will ionize. So this ionization will happen, complete ionization will happen at certain temperature. So the charge carriers with the ionization will increase at lower temperatures. These are the low temperatures. Okay, so there will be ionization at lower temperatures. Okay, and after that these all these are ionized at certain, let us say till 50 Kelvin. 50 Kelvin, all these these dopants are ionized. Okay, so the carrier concentration will be constant. Okay, so if we increase the temperature more and more above 300 Kelvin, because for certain temperature, so these electrons will not there is not sufficient energy for the valency band electrons to jump in the conduction band, right? So these valency band electrons will jump in the conduction band if they get the sufficient energy. If we increase more and more temperature, let us say 500 Kelvin, we are saying, okay, if we are, so then at that point we increase the carrier concentration, intrinsic carrier concentration will be increased at that point. Okay, because intrinsic, we are saying intrinsic because these are from the semiconductor, not from the dopants. And in this region, it will act as a extrinsic semiconductor. In this region, the partially ionization has happened in this region, and in this region, we have supplied so much of that energy so that the electrons from the valency band has moved from to the conduction band more, which exceeded to the dopant concentration. Okay, which exceeded to the dopant concentration. Okay, if there won't be any dopants, okay, if there won't be any dopants, so what would happen is, so if there won't be any dopants, this is the intrinsic carrier concentration. Okay, this was going like this with increasing the temperature. At lower temperature, there is no role of the intrinsic carrier concentration. Okay, so but at higher temperatures, intrinsic concentration will dominate the dopant concentration. So this is the thing. So now for today I have built till this one. So if you have any doubts, Teja and Sanjeev, so if you guys have any doubts, you can ask me. If you didn't understand in between or something, so sorry, my throat is paining, but still I have to do this. So if you have any doubts, you can ask me. Although my voice is not that much clear, I will try to solve your doubts. Sanjeev, Teja, okay. So I assume
No doubts.
no doubts. Okay, okay. From lectures itself, you can ask if you have watched the video lectures. Okay, so this is a different.
No doubts, sir.
Okay, okay, Sanjeev, fine. Okay, so that's all for today. Thank you for joining the lecture. So you can leave the meeting if you don't have any doubts. Thank you so much.
Thank you, sir, for giving lecture.
Thank you.